Hi, I'm Yinkai, and I'd like to share with you a work I have with Narayana Rangaswamy on weight distribution of classical codes influences robust quantum metrology. Now, this talk is a problem in quantum metrology, and first of all, I'd like to introduce to you the problem in quantum metrology in the noiseless setting. Now, quantum metrology uses a probe state in order to estimate an unknown parameter chi. And the information of this unknown parameter is extracted by performing measurements on the evolved probe state. And in this case, the evolved probe state is known as the encoded probe state. Measurement leads to obtaining a probability distribution, and from this probability distribution that depends on the parameter that we want to estimate, we can obtain an unbiased estimate on this parameter. Of course, we want to get the best possible estimate of this unknown parameter, which means that we want the variance to be as small as possible. And in order to achieve this, we can do two things. One is that we can, for a fixed probe state, optimize, find the best possible measurement that we can use. And second is we can also further perform the optimization over the probe state. In a noiseless setting, when this h over here corresponds, when this unknown parameter that we want to measure corresponds to the unknown magnetic field strength in a certain direction, then the optimum probe state is given by a GHZ state. This GHZ state, however, is vulnerable to noise. Even a single erasure error or dephasing error can render it a completely classical state. So any quantum sensor that is built based on this, when you have noise entering the picture, will entirely lose its quantum advantage. And this is the problem that we wish to address, we wish to study. We wish to consider an initial probe state and allow some noise to act on it. And then we allow this information about the parameter we want to estimate to encode the probe state, and then we do some measurements to extract the information about this unknown parameter over here. The probe states that we are going to use are going to be motivated from these classical codes. The noise model that we wish to consider are erasure errors. Erasure errors erases qubits and lets us know which qubit it has erased. So for example, if one erasure error has occurred on 7 qubits, we may, for example, know that the 3rd qubit has been erased. The resultant state is thus just a partial trace of the original state. The lower bound that we wish to obtain is on the quantum Fisher information. The quantum Fisher information quantifies the variance that we have on the parameter that we want to estimate. In particular, the quantum Fisher information is the inverse of the variance of the parameter that we want to estimate. The quantum Fisher information has a nice lower bound given by this linear combination of traces. We use this lower bound as opposed to the exact form for the quantum Fisher information, because the exact form for the quantum Fisher information is quite complicated and depends on the full spectral information of the encoded probe state. Whereas for over here, all that we need is the initial probe state, in our case, the noisy probe state, and a generator that we consider. And in this case, the generator that we consider corresponds to that of magnetic field sensing. And in this case, it is just the sum of Pauli Z's. And each Pauli Z afflicts only a single spin. We consider this generator acting on only n-t particles because we consider t erasure errors. So out of n qubits that we use for the probe state, t qubits are lost. And we use the remaining n-t to for our quantum sensor. And the question we like to answer is whether we can have a noisy metrology with what is known as a Heisenberg scaling, which means that the quantum Fisher information scales as quadratically with the number of the probe states. And over here, the number of erasure errors, we let it be constant, and the number of probe states, we allow it to grow. So the classical codes that we consider are binary classical codes. Let's give a simple example of what our probe state looks like. When the classical code is just all zeros or all one state, the probe state is just the Z state. When the classical code has some different code words, then the probe state will be just the uniform superposition of these code words. So given any classical code, we can write down a classical, a quantum state in this form, and this is the probe state that we wish to investigate. We wish to investigate how the properties of the code affects the performance of this probe state for the problem of robust quantum metrology for sensing the magnetic field strength of a magnetic field with a known direction. And for this, we need to define what happens to this classical code after some qubits are erased. Say the first qubit is erased. Then we would like to pick out all the code words in C that begin with 0, and also all the code words in C that begin with 1. And we call these codes C0 and C1 respectively. The properties of C0 and C1 will allow us to say how our probe state is going to perform for this quantum metrology problem. In particular, given any classical code, you can apply this partitioning of this set into two subcodes. Well, C0 and C1 are obtained by the previous procedure. For example, if the first bit is erased, then you have C0 to correspond to the code words that start with 0 in C and the code words that start with 1 in C. You can iterate this process and obtain the subcodes C00, C01, C10, and C11. So what is important and what we need for our main theorem is that if we have, for example, 2 erasure errors over here, you want these subcodes to be all disjoint sets. And this condition is guaranteed whenever the minimum distance of this code over here is at least t+1. So in general, we can write our probe states from classical codes in this form over here. And as in the case of a single erasure error, say on the first bit, we can obtain the subcodes C0 and C1. And recall that all that we need is for C0 and C1 to be disjoint subsets. Well, regardless of whether C0 and C1 are disjoint subsets, we can always write the partial trace of the original probe state in this way, where these quantum states over here are just uniform superpositions over code words in C0 and C1 respectively, and this Z over here is equals to 0 and 1, and in general it's just a binary bit string of length t. The probabilities here are just the ratio of the sizes of these subcodes with the original code. Now this decomposition over here is not a spectral decomposition when these quantum states psi of z here are not orthogonal, but they will be orthogonal if you have this t-Disjointness condition satisfied, or well, if you have the distance condition on the original code here satisfied. And once you have this written as a spectral decomposition, things become much easier. For example, we can make use of this fact. Recall that to calculate the lower bound on the quantum Fisher information, we need to evaluate these traces. Essentially, it amounts to evaluating what the action of this generator is on a computational basis state. And it's quite trivial. It is just related to the Hamming weight of this computational basis state. And together with the t-Disjointness condition, we can obtain our main result, which is the lower bound on the quantum Fisher information. Now, let me explain what our lower bound is about. Suppose you have a set of qubits that are erased. t qubits that are erased, and their labels are J1 to Jn, Jt. Now, this term over here corresponds to the quantum Fisher information after erasure errors on these qubits has occurred when we use a quantum probe state constructed from this classical code C over here. Then this quantum Fisher information after the T erasure errors occurs is at least a constant multiplied by a linear combination of variances. And these variances are precisely the variances of the weight distributions of the Hamming weights of the underlying subcodes that I've explained earlier. So what this tells us is something very interesting. As long as the subcodes, as all of the subcodes have a variance that scales quadratically with the number of particles that we use, then you can recover a Heisenberg scaling. Based on this intuition, we can have this, we propose the following construction. Let us start from any classical code, which we call the outer code. And then what we're going to do is we're going to concatenate this outer code with a repetition code, which means that for every code word in the outer code, we're just going to repeat the symbols. If you have a 0 in the outer code, you're going to put more zeros here. And if you have 1 in the outer code, you're going to put more ones here. And what you can see is that the variance, regardless of what the variance of the original, of the subcodes in the original outer code is, as long as you concatenate with these repetition codes, the variance of the outer code can be boosted by a factor of n squared intuitively. And this leads us to the following fact. If you have an outer code and you concatenate it with a length r repetition code, then the quantum Fisher information can be boosted by a factor of r squared. And so if r is linear in n, we would have this Heisenberg scaling. So what this means is that as long as you have a classical code, or rather, as long as you have a probe state that arises from, for example, a CSS code that has a non-zero quantum Fisher information, then by applying this concatenation procedure, we can boost the performance of this CSS code to achieve the Heisenberg scaling. Yes, and this boosting lemma can basically work when a constant number of errors t is erased. But there's a question: can we correct more? I mean, can this lemma can this main result be more robust to more errors that occur? And the answer is yes, as long as the errors, additional erasure errors that occur, have this bursty nature. So for example, even if the outer code is designed with to correct only one error, you can have just one block being completely destroyed, and this lemma will still hold. So as long as the erasure errors occur in bursts, we can have this Heisenberg scaling. And we compare numerically our results with other code studied for the same problem of robust quantum metrology, and find that the performance of a Reed-Miller code when concatenated with these repetition codes has almost the exact same performance as these permutation invariant codes, which can correct one error, and they perform slightly worse than those than permutation invariant codes where you can detect one error. But essentially the same scaling. And what we can see over here is that as long as you have a sufficient number of qubits, you are over this gray line over here. And this gray line indicates the baseline that we want to beat in order to have a quantum advantage. So anything above this gray line over here signifies that using these probe states, we can have a quantum advantage for a fixed number of erasure errors. And in this case, we consider 1 erasure error. So if you have 100 qubits over here and you have 1 erasure error, you're actually doing quite fine. And for future work, it'll be interesting to consider other types of quantum Reed-Miller codes boosted with this concatenation technique and study its performance for robust quantum metrology, and also consider the use of other concatenated quantum error correction codes. We could also study the performance of these classical coding expired probe states for other types, sensing other types of signals, and also applications in actual physical systems. And with that, I thank you for your attention.